Liu. It's a pleasure for me to be here. I want to thank you all for your attention about the optimal design of the heat integration system for freshwater production. So my study is optimal design for freshwater production through heat integration of solar heated membrane distillation and fuel cell system. Okay, it's divided my presentation into 4 parts. At first, introduction, some reason why I did this project. And second, I think about the research method includes this system architecture, process, and optimization methods. And then I will introduce the research results. And finally is my conclusion. This is my introduction section. And the membrane distillation system technology is determining the production of fresh water by different temperature. Therefore, many scholars have studied the issue of different heat energy source. Common use of renewable energy and the waste heat combined with the membrane distillation system. So the waste I used due to the unable supply of the solar radiation. The waste heat from the protein is the exchange membrane flow cell is coupled with the original solar conclusion in my study to increase the production of fresh water. No matter which system, you have to consider the system cost and the fresh water production. So it's necessary to optimize the unit size or operating conditions of the system to make it economical. This is my research method section. And then my research method is shown this flow chart. The step 1 is the mathematical module of each unit of the 2 systems in MATLAB and the simulate plan form. The step 2 is I verified the DCMD module using experimental data from the literature. After conforming the DCMD module, I should simulate realistic operation condition. I will give the environmental data for the dynamic prelimination simulation. And the last one is the optimal design for 2 systems. And then in my study, there are 2 systems. One is the solar heated DCMD module system, and the other one is the PEMFC coupled with the solar heated DCMD module system. And they are composed of 2 kinds of the circuits. The left side is the closed loop primary circuit, and the right side is the secondary circuit. And they are different on the PEMFC C is the behind the exchanger tank, a hot heat storage tank, and to increase the production water. And the system can use the waste heat compression by PEMFC to improve the seawater temperature and its water production. Next is the purification results of the DC&D module in my study with environmental data from the literature. We can see the different feed flow temperature and experimental and the simulation results are the consistent, and then see the different feed flow velocity results, the feed flow velocity and the feed flow temperature increase, and the arrow is the increase. And then, after confirming the correctness of the mathematical model of the DC&D, a preliminary simulation test will be carried out, which will be simulated in combined with the real environmental temperature and sunshine data in Taichung, Taiwan. In order to solve the uncertainty of them, in my study used the annual average environmental data. And my preliminary simulation to calculate the solar corrector and the heat exchanger outlet temperature, TFO and THO, and the heat storage tank temperature, TX. And the simulation result shows when heat storage tank initial temperature not equal to the end temperature, and the solar corrector outlet temperature is more and more higher. Of the 7 successive days, the system doesn't confirm the correct maximum temperature inlet and doesn't safety the community for day-to-day operation. Thus, my study has these limits in my optimal design. And next is my optimal design methods. In my study, I used the two methods. In my two methods, one is the admin function, and the other one is the full range search. Set the design variable initial points and range, and substitute the value into the formula that builds the unit module to calculate the TAC or TDP, and then you can calculate the objective function UPC and consider this constraint. However, repeat these steps with different initial points to calculate different UPC and find the lowest. And how we can find the design variable initial point and range? We can like this picture, and we can set the optimal, assume there are two optimal design, and the range set from x0 to xn, and that is the space a fixed value to design the initial points. However, is the optimal combination of the initial point safety the constraint. The TDP is calculated can equal to the original, and the is the opposite situation. The TDP is calculated get maximum value and can get maximum UPC. We can determine which one is a feasible or infeasible solution. And this is my research results section. And my research results include 3 results. And one is the DCMD module spatial analysis. And we can see the big picture show the temperature variable results from the simulation, or this is my simulation results, and this is from literature. And we can see 2 results are consistent. And then is another one is sensitivity analysis results. The systems and sensitivity, we discussed the relationship between this parameter of 2 systems in this figure and the membrane inlet temperature is the THO and TST, and water production. And because the use the different symbol and in different systems. And the right figure is the sensitivity analysis results. The results shown in the different values that between the maximum and minimum parameter value are in direct or inverse proportion for distillation production. Therefore, I decide to list the parameters that increase or decrease more as the optimal variable in the optimal design. And the last one is my optimal analysis results. And due to the time constraints, I only explain the second system results. We can see the second system UPC result. Use the Eppington methods. Due to there are 5 optimal variables in the second system, I fix 2 variables in the system, and the other are played the UPC. We can see the UPC results. They use Eppington method when the heat storage tank initial water temperature increase and the heat storage tank size increase and the PEMFC active area decrease, and we can thus this initial combination can find the lowest UPC. And using the full range search method, when the system fixes the solar corrector and heat storage tank initial water temperature, we can find the lowest UPC and this initial combination. And this is my conclusion section. And we can see the optimal combination safety, the community for day-to-day operation. The PEMFC coupled with the solar heated DCMD module system fails to the UPC, but it can have more stable heat source and increase the TDP for the original conclusion. And according to the TAC analysis, the PEMFC must be powered by hydrogen, and its price can affect the UPC of the system. if the hydrogen price can be less than $3 per kilogram, and the usage of the two-second system will be less than the optimal system. And in my future work, in order to reduce the price of hydrogen, we can use PV and electronic cells to granulate hydrogen and supply to the fuel cell, or replace the fuel cell and use the other industrial waste heat to with PV for distillation system from the natural. And then the end of my presentation. Thank you for listening.
Thank you very much, Dr. Yu-Hsin. So I open the floor for questions or discussion, confirmation, suggestion. Nobody? I want to ask one simple question.
Okay.
What is actually the privilege or the use of heat for membrane?
Yeah.
Please explain. What is that? What is the privilege of this heat induced for membrane?
I use the PMFC, the waste heat, and combined with the membrane distillation system.
So if this membrane be heat, it will be better than it is not heated.
Yeah, and we can see the research, and you can see the water fresh water production can increase the and
What is the material of the membrane? Material of membrane.
material.
Of the membrane.
Because the simulation the system big system, so I doesn't consider the material. Yeah.
Okay, thank you very much. So let's give big applause for Dr. Yu-Hsin.